and Dr. Eugene Kagan. Thank you very much. It's pleasure and cold being in Moscow in this time. I will give a talk. It's a free talk, so you can stop me and ask questions. We met some of the guys earlier this year in Israel. They came to meet, and we talked about our company, CB4. CB4 was founded after 10 years of research in the university and stays in close cooperation with Tel Aviv University, where I am a professor. Dr. Eugene Kagan is from Tel Aviv University, Dr. Gonen Zinger from CB4. And we work with several companies. The main idea was to create a software that can do analytics automatically in order to deal with the large amount of data that we are facing. And the company won IBM Smart Camp in Israel and will compete in 2 months or in a month and a half on the world title in San Francisco. We have a large body of customers. Sometimes we just put the engine which does automatic identification of patterns to different industries, and sometimes we really create solutions, and when we create solutions they are really focused on retail and e-commerce. But do I have a pointer here? No, oops, no pointer. Okay. Okay. The outputs are represented in screens when we talk about solution. For example, Eden e-commerce solution, we translate these Eden patterns to business rules so that the people that have to work with the data will get an idea how to use it for the business. Sometimes we face application of demand sensing and Eden anomalies. So there are several modules in screen to basically translate the output of the model to a business language. I will talk in a moment about the type of applications that we are working. I cannot say too deep what we are doing, but at least the taste of the algorithms that we are doing are based on the idea that today, with such an amount of data, what you really want to do is to be able to create a server that each time that it meets a pattern, either in time or in space, it will create a relation. And it's basically an optimization process that if the pattern is enough significant, it will be stored in the model. And what you end up what you end up is, and this is an example, for example, of a model that represents browsing for e-commerce in the internet. So you can have variables that are related to the user type and to the last login and to the login time and so on. And what you end up really is with a model that can be very personalized. It can reflect a specific user, a web page, a specific server, and actually store all the relevant pattern that belongs to this object. This is just an XML presentation. Of course, it has another presentations, but at the end, the meaning is that instead of trying to find model, conventional, for example, a conventional time series model that reflect the behavior of people browsing in internets or people or products sold, and trying to do a fit of modeling, hypothesis testing and modeling, what you have at the end is sometimes millions of these models that can be represent very clearly this object. And with this type of models you can do many things. You can do anomaly detection, you can do clustering, you can do classification, you can do business rules and so on. So the main idea is to be able, once you do this modeling at the system, at the user level or at an object level, is to give a fingerprint for each object and to find all these hidden opportunities that when you do conventional modeling, you cannot take them into account, but when you do a specific modeling per object, you can find them. And this is the main philosophy. Now I will introduce some of the ideas of basic idea of the modeling, what is required, and I will use some of the old publications. And although I cannot go into deeper know-how of how we do it, the concepts are very similar. So this is just, I'll show you a picture, which is which you have to guess when you can what is there, and we'll try to understand what is a key feature that we ask for a good modeling. Okay, so here we don't say, you look, here I gave you a 5-order model you didn't recognize. Here you see that we don't get a lot of information at all. But here look what happens. Okay, all of us know it, and if not, then it's clear, okay? So what we can learn about this learning process, this identification process, and we do not do image processing, but I just want to take into account what happened now when we try to identify a pattern that, in this case, it's a Mona Lisa. So we have a probabilistic model. In this case, it's the colors of the pixels, okay? So first you can describe it by a probability model. Then there is a relation between the color of a pixel to the neighborhood. So for example, if there is a bright color, it will be associated to other pixel with a bright color. If not, if it's a random picture, and then you cannot compress it, of course, and it means that there is no information in it. Now, the dependence structure is very unclear. It's not something linear. It's not something. Sometimes the dependence is between the pixel to the right side. Sometimes the most influencing pixel is the one that is on the upper level. And it is of variable memory order. Sometimes I could be in an area when I add more and more and more pixels and you do not get any new information. And sometimes I just go into a place where there is a change and you get a lot of information and it's of a variable order. Sometimes just by 2 pixels you can get most of the information and identify what patterns you have there. So these are the type of principles that we look in modeling of real phenomena. We look something that can decide which type of order and context is relevant in different area in the pixels, in the picture. So think about areas in the picture that are reflected by different random variables. So sometimes you need a lot of information, a long memory order, sometimes you need less memory order, and you can gain information specifically in area when this distribution change. When the distribution change rapidly, you can gain more information. And this is a type of principles that we are looking for the modeling. Now, we work close to this area of Bayesian network. It's a known area started by Judah Pearl 30 years ago that give a description of the relation between random variables. This is one of the old stories. If there is an earthquake, you will get an indication in the radio. It will ring an alarm. If there is a burglary in the house, it also will ring the alarm. Then you will get a call. And the question is how you can represent the scenario, the joint probability distribution of all these variables. Now, the Bayesian network provides you with two things. First, it's a qualitative part. It's the structure that sometimes you know. For example, here I told you a story which makes sense that, if there is a burglary, then there is an alarm, and then I get a call. sometimes this structure is unknown. By the way, in most of the cases, in reality, this structure is unknown and you have to learn it. Now it is also a quantitative part, of course. It's the probability, the joint probability distribution that is related to the nodes. I should say that it's a directed acyclic graph where nodes represent, if I didn't say it by now, random variables, and the edges, the influence or the causality, it doesn't matter, between these variables. Now, even, and I'll show in a moment that by this description you get a lot. By the way, how many people here are familiar with Bayesian network? Okay, so I should move fast. Okay, so not only that you get by the composition and factorization a lot of get rid of a lot of redundancy by using Bayesian network, but even here you can see, and this is just a hint for the next generalization of the network, that you see that, for example, if you know B, if you know that there is a burglary, actually you don't need to know anything about E. In any case, these are the same probability distribution. That means that probably you can delete some of these parameters out, and it means that you are there is a less dangerous for overfitting. You better treat the variance bias trade-off. You are much better if you know which type of parameters you want to delete. And as I mentioned before, and since most of the guys here knows, the main advantage is in the factorization, the fact that we have conditional dependence or conditional independence between the random variable. And when you do factorization, instead of having all the full probability distribution, you can just take only those that are represented by this Bayesian network that was either given to you or you learned it. And this, of course, reduces the complexity sometime in order of magnitudes if you have the number of parents per each node much smaller than number of random variables in the case. So this is the message of a Bayesian network, and let's take a look how we start with a simple modeling and we can make it more and more complex. So you can think about a case where you have independent random variables, and then this is the model. Simply each one has its own distribution. Now you will get a new sequence of data, and you want to find the likelihood of this sequence. How likely is it it appears in the data, whether is it a normal sequence or not, to do an anomaly detection. This is the likelihood that you will apply given this model. Now, of course, you can think about a case where you have a fixed order dependence, like a Markov model. Doesn't have to be of order 1, like we see here. It can be of higher order. And this is the way that you will encode a new sequence that come to find how much likely to belong to such environment. And of course, you can do the Bayesian tree, which can be found. It's this structure to find the most likely Bayesian tree is a known problem with an optimal solution solved 40 years ago, and this will be the structure. But if you want to deal with real problems, you have to go further than that. You have to address Bayesian network, as I mentioned before. And not only that you have a problem here, because to find the best structure of a Bayesian network for when the number of parents is larger than 1, it's a very complex problem that is not solved fully. So you have to use some kind of heuristics, either by the composition or EM or genetic algorithm, and many people are working in different with different algorithm and heuristics. I will mention Williamson later because this is one of the things that we do. But let's say that you found somehow this structure. What you can really do now is to, as I mentioned before, to find not only the dependence but the context-specific dependence of a random variable given its parents and the actual realization. That means that, for example, if you observe the x2, it's not enough to know that it depends on x4, but somehow you can find that it only depends in x4 if x4, and I'm talking here about the case of DNA, only if x4, which is a nucleotide in a position 4, is either of type A or of type T. If it's of type C or G, then the distribution is about the same and you don't need to account for these parameters, as I showed before in the small example. Now you can think about random forests that are represented by these type of trees. Now you can think about different weighting of these random trees to represent actual phenomena. Now you can think about filtering and mapping. So this is a level of complexity that you can grows higher and higher. And the problem, of course, there is no free meal. The problem will be in the learning. So if I give you this model, maybe it's the best model that you can work with, but the real complexity is now to try and build this complex model that has a lot of degrees of freedom to represent the reality. And this is exactly what we try to do, many steps above this one, when we built our complex structure. So I can summarize and say that, you know, you can think about homogeneous marker models that are fixed order, no position dependent, meaning they can be non-homogeneous, homogeneous, and with a known structure. And you can go up to this area when you have variable order, context dependent, position dependent, unknown structure, and all the filtering and notes that I gave before. So I will skip the part of how to optimize and to find these type of models, and I'll show, once you have this model, what type of information you can get out of it and how it represents nicely the complex phenomena. And I'll start with just an example, something we published a long time ago at Bioinformatics, when we tried to find models of DNA segments. You know that DNA is translated to protein, and then all these nucleotides, each triple of them can be translated to a codon. And actually, if you find, and this to amino acids, to proteins, so if you find, you can find the in the nucleotide level the significant patterns of nucleotides, you can say something about the proteins. And the particular problem we try to address with biology people is what they call transcription factor binding site. These are places before the coding area where the mRNA binds into the DNA and all the transcription starts to evolve. So if you know these two places, if you are able to identify these two places, it has a lot of meaning, because sometimes you want to close this area. It's like a key to the DNA. If you close this area for some time, for example, diabetes medicine, if you close this area by binding a pseudo mRNA here, it will stop, it will close this area, and you cannot do a transcription of the coding area. And of course, if you can identify them and you want to enlarge and to promote this transcription, it also helps you. So this is the importance of these type of areas, these TFBS. And the nice thing about them is that they are very short. In this case, we had the 12th position, and very structured. So data is very structured. And although it's very small and very structured, it seems that with this amount of flexibility of variable order Bayesian network, you can get squeeze out of this data. I will show a data of DNA, more information than you can do with regular modeling. And this is a nice thing, because everybody knows that if the data is complex, as the data you deal with Yandex, then complex modeling is needed to model them correctly. But here the nice thing was that it was really simple, just 12 codons. 12 nucleotides, very structured. And we had the best result in the literature. And we showed that with an extra amount of flexibility, you can get out of it more information. So we did what we call VOBN. It's the type of modeling that I showed before. When you map the area of classification, it belongs to supervised learning, to probabilistic model, because you have other that deals with logical rule, and to models that have unknown structure, particularly to Bayesian network, and we did this extra generalization. Now, just to mention that usually people worked in this problem. The best model was this one, which is a very simple model. I'll show in a moment. Now, when people tried to move from PWM, which is a position weight matrix, it's just simply saying that the distribution in any position of the nucleotide is different. When they jumped to Markov model, it was already overfitted, because they had quite a few samples of data, and it seemed that this jump already deteriorates the true positive rate given a fixed true negative rate. But the nice thing about it, and definitely if you go from Markov model to something more complex and you have more parameters, then you will meet much earlier the overfitting. The nice thing about this research was that when you did this variable order game and you enabled to choose the Bayesian network only for specific scenarios, then suddenly you could reduce, you could in one hand keep the flexibility, but in the other hand reduce the amount of parameters and find something that works better than that, and it's more complex than that. And this is where...
Could you explain
yes.
a little more about what is it position-weighted model?
Now I'll give an example. Step by step, this is exactly what I'll do. So first, what we need to do is very simple. We have data that we took from, this is E. coli, you know, something that goes with all of us. So we have E. coli data of these, of non-TFBS, of this binding factor. And we have places that we are sure, places of non-coded area, that no binding sites exist there. So we have, it's a supervised, simple supervised learning of positive and negative samples. And now your mission is, when you get a new string of data, is to decide whether it belongs here or there. Now take it to Yandex case. Maybe these are good customers and bad customers. You want to identify to which one these customers belong. And this is a customer with multi-attribute data. What time he entered the internet, what last buys that he did, what was the last conversion, what was the last click, I don't know. But the problem is a classical problem. And in this probabilistic model, the idea is to build a model for TFBS and a model for non-TFBS. And the question is which model to use, and we will use quite the one that I mentioned before, and you'll see exactly the difference. And then doing just log likelihood ratio in this case to decide where this new codon belong. Now, when you look at things that people are doing, so first it's what they call consensus. They simply look at each position. They know, by the way, they know very well that each position has a different feature and should be modeled differently. So this position-dependent structure exists in all the good models. So what they do a consensus. So if here there are, you know, a majority vote, or in internet you have, you know, if you go to Amazon and most of the guys that bought this book bought another book, you'll get this type of recommendation. So basically this is a consensus vote, and it performs very bad because actually you lose a lot of information. You don't get any information for the actual distribution there. You don't get any information about the structure there. So it's not a good way to do it. Then you have a homogeneous Markov model. It means that you take all of them as a sum, and you try to ask yourself what is the probability to get an A, what is the probability to get a B, a C, a T, a G, and you end up with, 4 or 3 parameter, 3 independent parameter, and you can actually, when you have the new sample coming, you can actually provide the likelihood, and it performs actually bad as well. And of course, it performs bad because it doesn't take into account all these structures. If look here. Here, it's always a T, no matter what comes before. But there are some places that where whenever there is a G here, there is a T there. Of course, it misses that. It assumes no dependence. So of course, it's a bad model. Then there was the model that was the winner before we published this paper. By the way, I don't know if now they have a better one, a better model, but this was the best model when we published it in 2004. They simply took the distribution at each position. So think about, you have good customers that go into internet, you have their features, and now you just do the distribution of the realization of each variable. Okay, so this is the idea. So in position 1, there is a 33% that it will be either A, C, or T. However, in position 5, it's always a T. And so on and so forth. Now, this is much better than the regular Markov model because it takes into account the positioning. But as you see, that since it's a Markov order 0, this is the PWM, is the Markov, is a probability weight matrix. It doesn't take into account any conditional dependence. So what you can do is to find the parameters at each position. So you have 12 position times 3 parameters, and you can actually then, when you get the new string coming up, the likelihood will be computed like that. You will find the probability to observe the A in the first position times the probability to observe C in the second position, and so on and so forth, and you'll get a likelihood. It performed, as I mentioned, the best. It was the best model up to that moment. Yes.
Can I ask a question?
Sure.
How is this matrix Markov model if each cell of this matrix doesn't depend on the?
Yeah, this is why it's Markov 0. It's Markov 0. It's Markov 0. You are right that we shouldn't, definitely not here close to Moscow University. Okay. My advisor, Lev Levitin, was from Moscow University, and I shouldn't say that it's Markov 0. He would cut my head off. But this is the way to say Markov 0. They use it in bioinformatics. They use Markov 0. It's the same as PWM. You are talking about Markov of order k. This is definitely the Markovian property. Here, let's say that it's order of 1, and then you see that this is actually the modeling that you know. And the problem here, and I mean, now it's position dependent, so it's inhomogeneous. Second, it has an order. That means, and we did all of them. It starts with order 1, then you can take into account second order and third order. Now, for us, it's very clear that it should reflect the behavior of these TFBS much better than the other model. Definitely better than the PWM, than the Markov 0. But in fact, the problem is that by definition, since you have to carry out with you so many parameters, it ends up with overfitting. So the jump between PWM that doesn't take into account any dependency, even to Markov 1, that adds to its position 4 times 3 parameters, it's a too big step. It's a too big step. It adds too many parameters and it kills the model. So Markov 1 was worse than PWM, and definitely Markov 2 and 3 were overfitted. So this is variable order Markov, it means that you can actually, it's both, you can take into account the dependence only if you find that such a dependence exists. So for example, in position 5, you don't have any children, so to speak. You don't have any leaves because you have a probability 1 of this position to be a t. So you cut some of the parameters and it gives you a better result. Now, this is the way that now you have to code it or to compress it or to find the likelihood. For example, you know that what is the probability to get an A in position 1, and then in position 2 you know that it depends on A. So depending on the value of A, you find the probability or the likelihood of obtaining a C and so forth. But the variable order Markov model doesn't have this structural, it has a fixed structure. It always assumes that the nucleotide to the left are the one that affecting the other one. Now in reality, it doesn't have to happen, of course. You know, first in genome, what you have these coding, they have a complex structure when they code to proteins. So maybe the 6 nucleotide affect the first one, and then the 5th nucleotide affect the 6th one. So it doesn't have to be in a certain order. And of course, in real world, when I said, for example, this you have a new client, a new user, and you have these variables, you never know the structure of dependence. You have to reveal it. You have to find it from the data. So this is a VOBN. So first you find the dependence by using method. If it's a tree, you have a clear way to find the best tree that will yield the most likely, the highest, that will maximize the likelihood. And then per each position, you have the same variable order, but now, you know, it doesn't. So position 2 depends on position 1, but position 3, for example, depends on position 5. So you had more flexibility there, and you cut it if you don't find that these scenarios, the real data, supports this dependence. And this is the way that you have to code it. And this was indeed the best model. So in one hand, we add a lot of flexibility to the model. Suddenly, the structure could change. It shouldn't be only a tree. The specific realization could reveal whether it will be dependent or not. So you got a lot of flexibility in the model with a relatively small amount of data. And although the Markov model was too complex, even when you did the Markov modeling from PW, it was too complex. Here, since you could reduce the non-relevant parameters, it ends up to be the best. And the biologists we work with, their performance measure was to maximize the true positive rate for a fixed true negative rate of 99.9%. It means that, you know, they are very usually what they have is in vitro, in vivo type of measures. So they scan the genome by these type of tubes. If they find a case that they think that it will be a potential to be a TFBS, they will analyze it much more thoroughly. So they want to be sure that when they decide that it's a non-TFBS, that the error will be smaller than 0.1. And when they decide that a region is a TFBS, they want it to be as likely as possible. They want to maximize this probability. So this is the VOBN. This is how when you treat, you have both the background and the foreground. You have because when you do a likelihood, you have a likelihood of the positive samples of the negative, and you do a likelihood. So you can plot the likelihood as a function of both model. In this case, only 2. Sometimes in reality, much more than 2, but of this model. And you see how it behaves, and you can find what is the highest position. And in this case, we were able to take the best model of all of them was, as I mentioned, the PWM with an order of 43.5% of true positive for a fixed true negative, and raise it by 4.3%. It means that if you have 4,000 genes like E. coli, you have 172 potential genes that you can discover. This 4.3 means a lot. I don't know, it's like a conversion in your case when every 0.3 is relevant, but here it means to bioinformatics. So another example that we did is to try to use this type of models. I will go very quickly to find if markets, and the idea that we did markets is but because you have a lot of data and it's free, if markets are efficient or non-efficient. You know that the weak form of the efficient market hypothesis says that you can always do some good prediction when you want to predict the value of the stock market, but it's only for a limited number of time. If information is efficient enough, then the price of the stock holds all the information. Actually, you cannot do more than that. You cannot apply algorithms and find points of inefficiency, which means that you can make access return, you can earn money. Point of efficiency means that people do not know something that other people know, and they can take advantage of that. So usually, by the way, in reality, what happens is that there is a competition between financial groups, and there is, in many cases, small window size when someone invents a good algorithm and it can take some advantage of this inefficiency, but then after a while this information is it's absorbed to other places, and then you cannot get access return out of it, and so on and so forth. So what we did, we took data, we applied this type of modeling, and just to show you that it was very clear, there are 4 stocks market that we checked: Vienna, Copenhagen, Frankfurt, and New York. And it was very clear that when you talk about the larger markets with a lot of volume, they are very efficient. In very few cases, we could do a little bit better than we can do a prediction which would result in a profit. In most cases, not such prediction is available. Whereas in smaller markets, where some key players play larger parts and the market is inefficient, you can definitely see that there are certain patterns there that if you apply them at a certain point of time, you can theoretically earn money. By the way, it's important to say that when we did this game, we didn't pay commission. So many of these efficiencies, if we had to do it real time and make money and pay to get the information and pay to do the transaction, it would turn into a loss. But theoretically speaking, you find here that these markets are inefficient, whether the larger markets are efficient, and it gives you an indication that the model can really reveal patterns efficiently in a large databases.
Would that be true that smaller markets are also efficient in terms that you cannot actually win any money in this market, considering commissions and stuff?
That's right. This, yeah. So it always, the big players know how to play it. So it's, you always find either a rule or some way or another that makes it very hard to make money in this way. I think that the best, we have some access to companies that work in this area. There are 2 ways that people try to make, or 2 main ways that people try to make money in stock market, either by prediction or by an arbitrage. And definitely the one that works better is the arbitrage. Because you have to, if you can know very fast that what happens in one market with the same stock is much better than the other market, and you can change it, then it's, you know, it's not a prediction. It's just you are much more efficient. And the other way to predict, it's much more hard. By the way, the good news or bad news, depends where you are, is that Obama legislation for this arbitrage, they now declared that it's for a certain point it's illegal. So large players will have hard time to do this arbitrage, because what actually happens is that big player, since they have very close and a fast access to the market, they gain more money just because they are richer. And the money comes, of course, from the simple people that buys this market. So it makes it, actually, it's a way to move money from simple people to organizations that have strong access to information and strong servers and can find this inefficiency very fast. And this is the thing.
Sorry, so did you tell that they make arbitrage illegal?
No, I'm saying that arbitrage is illegal, by the way, but what Obama administration now filed is a set of rules that if a financial organization is doing arbitrage up from a certain point and more, it means that it's illegal, or it has to go through approval, which is much harder. And the reason is because, as I mentioned, because actually it gives advantages to richer organizations. Okay. Okay. So so far we just talk about the modeling, but whenever I spoke about modeling, it was a modeling of a joint probability distribution of the whole sequence. Now, what happens if you have a very specific target? So, for example, you want to classify your customers. Can you do better? If you know in advance that you will use this Bayesian network for some purpose, can you know in advance a way that you can use it during the learning stage? Because there is the canonical approach. The canonical approach separates the learning from the purpose. You learn the reality as better as you can. So, as we did before, you find all the models, you crunch the number, you do hard work, you find the best model. Now, this is the best model that reflects your knowledge about the real joint probability distribution. Now you go to the second stage, and sometimes you need to do anomaly detection. Sometimes you need to do classification. So the purpose changes. Now the canonical approach says that forget, in the learning stage you do as better as you can. Now you take this model with you, and now you'll see what you need. You need classification, I'll use this model. Now what we try to do in this target Bayesian network learning is to take into account already in the learning stage what will be the purpose, and try to redirect the learning so that it is more efficient for the purpose. So for example, in classification, it can work in any function, but in classification, think about that. What you really want to do is to know the conditional distribution of the class variable depending on the rest of the variables. You actually don't care if, of course, I should say, if you don't have any limitation in time and effort, then definitely the canonical approach is better. If you can learn the reality as good as possible, do it. If you have limitation of time and of cost, and you'll have to sacrifice something, which is usually the case, then you have to decide whether I do the best canonical approach as I can, or maybe if I do a classification, it's less important to me to know that variables 6 and 4 are related, and I'm much more interested to see what will affect variable number 6, because this is the variable that actually I will be using in my optimization process. This is really the variable that I will be using for the classification, for identification, for deciding whether to take any kind of managerial decision. So can I take this information into account translate it to the probability terms and learn the parameters, those parameters that are more relevant to my target. So before I just showed models, now I'm talking about taking a data set and structuring it and building a model and asking whether to do it as best as I can from a canonical side or to do it with some knowledge about the purpose. And there are two main approaches in the literature. One of them, which is based on the canonical approach, and there are many very good algorithms that do it. They try from the beginning to do something which is in general can be described by this form. It's a general definition. Some of them represent it a little bit different, but what they try to do, they want to optimize the model, the Bayesian model, given the data. Maybe I should do a given. When you have two terms, one is to maximize the log likelihood and somehow to penalize the overfitting or the complexity of the model. And you have the AIC, the IKK information criterion, the MDL, and many other models. But basically what they try to do, they follow the canonical approach. They say, I will learn as best that I could the general model. I don't care what I'll do with this model. And the way that I will treat this trade-off is by somehow optimizing these two. So either they do maximization of the subject to some constraint, or they try to do a bio-optimization and things like that. There are other group of literature that try to do what is called target-oriented, the thing that we wanted to do. So they take into account from the beginning, and here I focused on classification, the purpose of the modeling. So in this case, these are target-oriented approach for classification. So they know in advance that they will need this model to classify. And in many cases, what they do, they use a fixed structure. So they take this assumption and they force it into the structure. So for example, when you took the most simple, the naive Bayes, what these people are doing, and naive Bayes, by the way, works quite good. It's amazing how good it works. But they decide from the beginning, say, I will put here the class variable, and I will try to learn all the other, how they affect this class variable. So they no longer have this kind of assumption that they want to do a trade-off because they assume a known structure. But this is a target-oriented. What we tried to do in this research is to take these two considerations into account. First, to do something which is similar to that. Somehow I'll take into account how complexity can affect. But second, take into account that at the end we need it for classification. So what we end up is it's a structure that as we add more complexity into it, it enables to get higher likelihood, but at the same time it gives higher probability or advantage or priority to the probability distribution that describe the classifying variable. So if I take, I mentioned before the Williamson approach, a classical approach in canonical, you have a true distribution P, you have some Bayesian network distribution Q, and you want to best estimate P. Maybe I should put a tilde here. And what they try to do is to minimize some distance measure here. It's a Kullback-Leibler. It's not a classical, it's not a legal distance measure, but it works very well. And it turns out that it is equivalent to maximize the total sum of mutual information among the weights. So they try to deal with this problem. This is the canonical problem of Williamson. And actually, Williamson does it not only to a Bayesian tree, but to a Bayesian network. And he's able to provide nice results. So now we try to be quite similar. So we have an unknown distribution P. We have a Bayesian distribution Q. But now, instead of estimating the overall general probability distribution, we want to maximize it first on the target variable, and the class variable I, given all the rest. X prime is all the rest of the variables. So we get the same structure here, but the goal is to maximize the conditional probability of the target variable. And it turns out that you can translate it to a two-step maximization problem, and in one hand provide a model that is focused on finding this purpose, this target variable, and on the other hand take into account this information constraint, the complexity constraint. So this is basically the main procedure of the algorithm. It's managed the error complexity trade-off by some information measure, but it can decompose this constraint differently, one for the target variable and another for the rest of the variable. And when you do so, you get this is maybe this is the image that explains it all. The canonical approach, just forget what I said, just focus here and you can plug back. The canonical approach does the following. You want to maximize the likelihood and to minimize the complexity. Now, it doesn't take into account that there is a class variable and the rest of all of the variables are the same. So basically it works on this line. This is what you see here is this is the accuracy or the likelihood, and here are the complexity. But the TBNL divided to the complexity of the rest of the variable versus the complexity of the target variable. So if you look at the canonical approach, this is the line that you go through. You start with the most maybe simple models, but you don't have any accuracy. And as you get more and more complex model, you can elevate your accuracy up to a moment of overfitting. But actually you work on this line. When you divide it to these two problems, separate problem, and you treat the target variable complexity differently than the rest of the variable, then you have now a two-dimensional decision zone. You can increase the complexity on the target variable and end up with something that looks like a Bayesian, like a simple Bayesian. I forgot the name. Sorry. A simple naive Bayes approach. Sorry, slipped me. So this is if you increase only the complexity on the target variable. Or you can just increase the complexity of the rest of the variable and get something that sometimes is not related to target variable. Or you can do the two. You can. It helps you to give more complexity or more effort to learn about the target variable and then associate less complexity to the rest of the variables. And this type of flexibility is of importance. And I will skip these. Where are the results? I'll show that we ran it on many databases. UBC databases. And what first one must say that there is no one dominant method that is better than all the rest. You see that the bold one, each time you have the C45, the TAN, the NB, many type of models, and you have here are the different databases, and this is the accuracy that you obtain. So you see that there is no dominant one. The TBNL, the one that we run, end up to be the best on the average. And actually, even if you consider the number of cases that is the highest, is advantageous on the other. And the reason is why we were able to get more accuracy than the others is because we have this. Now I can get back to that. We have this extra flexibility. All the other one only control the flexibility of the whole model. Now we can control the flexibility of the model separately the target variable and the rest of the variable, and actually we end up with some kind of a Pareto frontier that at a certain point get a higher accuracy for a given flexibility. So for example, this is a naive base. There is a fixed structure, and for the fixed structure with such a complexity, it gets such a level of accuracy. Now the TAN have some flexibility in the structure, so therefore you can use different structure and get the one with the best accuracy. Now the TBNL, since it has another degree of freedom, and you can actually allocate, not only decide how much complexity you will add to the model, but how it will be divided between the target and the rest of the variable, you get another layer of complexity, and you can find the area where it operates most. And you squeeze more out of the data. And this is another type of database devote, when you see clearly that in this case the TBNL is dominate from this point. For a given amount of complexity, it gives a higher accuracy, or another one, and so on. So there is no magic. The reason that we were able to squeeze more, a little bit more, out of these data set was that we just plugged in, we created another button from the user. So far the user had only this button that he can decide how much you want to increase complexity and see how accuracy increases, and then it's tried to decrease, so it stops there. Now we have two buttons. One, he increase complexity for the whole model, but he can associate how much will be associated with the target variable, how much with the rest of the variable. So now we have two buttons. He can actually play with it in the learning stage and find a model that is more efficient. So these are the things that we presented. I was asked to give technical. I don't know if it was too technical or actually not technical at all. But based on this type of models and actually models much more complex than that, we think that we can and will be happy to cooperate with Yandex to better squeeze from the data information about the persons, providing, for example, a unique fingerprint per users, and personal, even more the search results, or do a user profiling for e-commerce, or do monitoring and anomaly detection, and we hope that we can establish such lines. I will end up with a link to Procter & Gamble that work with us closely in the last 2 years, and we do a lot of things together, including e-commerce, and we are very proud of the outcomes of this cooperation. I will play it. I see that it didn't find it like that, so I'll open it here as concluding.
In P&G, every day we touch 4.2 consumers with more than 300 different brands. You can only imagine the huge amount of data that we need to analyze every day. And in order to do it in a smart way, we need smart tools that are capable of giving us competitive advantage in this area. What we like about CB4 solution is that they do not presume any prior knowledge, and the outputs can reveal complex patterns. For example, they can find that two products that normally are not associated with each other, like Gillette and Pampers, may behave similarly in a certain store under certain weather conditions. CB4 helps us better understand our consumer needs. It helps us optimize our supply chain and find the hidden purchase patterns when we use e-commerce. And I think most of all, they can help us see the key business drivers that can otherwise not be understood using just usual tools.
Okay, thank you very much. Open for questions.
You didn't tell anything about the learning step
About what, sorry?
About learn step. How to learn the structure.
Okay, so I gave some of the hints, but indeed to go into this technology deeper, some of it is under security. But I think that even from the beginning, when you look at the Mona Lisa picture, you can think about the type of features that you need to take into account when you learn. Variability, context dependent, structure independence, personalization. All these type of features can be advantageous when you deal with this type of modeling.
So the main two ideas are getting structure, and the second main idea is tuning their model to better suit their required variables.
These are two important. I don't think that there are the two. One is to get the structure when you know actually you can know in advance what is the goal, so you can take it into account while you learn it. Second, when you learn things, you need to provide for a complex environment, you need to provide a very complex ability of the model. You cannot, we were talking with the guys that do anomaly detection. So in many cases, you can work just with conventional time series approach. But if you think that the data, and this is the case actually, the data change in a very unpredicted way. The states, it's a state-dependent data. Suddenly there is a new service, ops, things change. If there is some kind of complex structure in the data, you need to provide this type of flexibility in the model. And it goes in many directions. I just named few of them, including the structure, including the dependency, including the modeling, including the scenarios. But actually, when you think about it, think how data can be complex and try to take all this into account into your model. Now, try to find how to optimize to get these type of models. And then you get the best model that can reflect this data.
By the way, I have one question about learning the model.
Yes, yes.
Is the learning process online or offline?
Oh, very good. So it depends again on the application. In many cases, yeah, it can be online. But when you deal with streaming data, many times you divide the two scenarios. And this is what can be done in many cases. You can learn it in offline, update it, but you can always maintain the grading, the decision making online, because once you have a model to decide what to do, whether to declare an anomaly detection or to classify it, this can be done very, very rapidly. And you can actually treat big data in real time when you do that. You cannot build such complex model in real time when you account of big data, and you need to do something smart to do it offline and to update it in real time. And this is a real advantage, yes.
So if we have some new feature that wasn't known when we built the model,
yes,
we need to rebuild the model, not merge it.
If you do it in the old way. In our case, for example, we defined the model rules, so to speak, and actually the client at any point of time can get new variables into the database or reduce the variables, and it is and the model will work with the variables that exist there. So we have a company that at a certain time decided, without even letting us say no, and it's perfectly okay, that they want to put in their database variables that reflect the weather, the temperature, the weather, the condition, and they found very nice patterns, and they didn't thought about it in the beginning, but the new patterns were learned, and you could do something smart with it.
But the model was relearned not continuously, but discrete. Old model, new model, not a continuous.
No, well, it depends. When you look at milliseconds, actually, yes, you are right in terms of the definition, but actually, when you look at it at delta t's, it's actually continuous. So
can we incorporate the weather changes data in delta t? It's
well,
it's more